So welcome to my talk on bias sampling. So this is a project which we termed as Blade, and I'm from Amazon India. So the problem that we're trying to address is product recommendation. So given a phone A, we would like to recommend other related products, which could be sold together with this product. The challenge here is that we would like to ensure that the directionality of the data, shown in green, the edges is preserved, during the learning phase, right? So how do we get this data? Customer interactions provide, options for us to, create this, multimodal data. So what we want to do is given any graph of this form in this context consisting only of products and edges connecting between these products by say co-purchases, we would want to learn the node representations. So in this context, this problem translates to what is called as node recommendation in directed graphs. So here we craft a problem setting as that we are having asymmetric relations, which is gone by the direction of the edges, and two, which is counterintuitive to an industry setting. Assume that we do not have any catalog data or any product or edge features available for this for every node. So what do you do and how and what are the various options? So these two are the primary challenges that we try to address in this paper. So what are the options that we have? So one is we can restrict, during message passing, the nodes that are picked up only to be, obeying the directionality. But the downside is that these popular methods are more or less suited for, undirected graphs. And secondly, when we want to have these embeddings learned, deployed for downstream tasks, you have an issue. That is, for a given phone, you want to recommend a phone case, but not vice versa. It will lead to poor customer experience. So that is the main challenge one. Challenge two, in the absence of product features and thinking of graphs that could go up to millions of nodes, going with a simple one-hot encoding embedding vector would not be the best way to go about. So there lies another challenge, right? So that's challenge number two. And one could, go about simple ways like coming up sampling from a uniform distribution or a normal or other such probability distributions. So they may not lead to the best performance, which we will show later in the experiments. And having a solution that that needs to scale to the setting is the whole challenge. So to address all these three things, we come up with a proposed framework which we call as Blade. So in order to handle this asymmetry, what we do is we go for two embeddings. For every node, we have a source and a target embedding, and which we use to handle the direction. And to initialize the node features, we use some sort of pre-training where we deploy a random walks, biased random walks, and generate the embeddings, for each node and feed them as input to the GNN during training. And for the scale, what we do is also to handle any potential structural bias, we consider the edges for every node or the neighbors for every node based on the degree distribution. At the end of it, what we say is we want to obey the following distribution, that for every node, we respect or we prioritize high degree nodes during sampling, and the low degree nodes have less probability of being sampled. So keeping these three directions, this is a toy example wherein on the left-hand side, if you focus on node A, on the left-hand side, if you look at the computation graph at layer one, you would see that A would have B C and E, which are the ingoing edges to A. So you will have these three edges formed, right? In the computation graph, the messages would flow in this way. But in our setting, we have a source and target embedding. So this is what we do. For for the source embedding of any node, which we represent as AS, you take all the out edges, which is E in this case. So we have the message going from AS to ET. Similarly, when you're trying to learn the target embedding of AT, you actually have ES, CS, and BS, which will be the participating in the message passing. And the idea is when you want to estimate the importance of an edge AB, you would just take the dot product of AS and BT. And similarly, when you want to find out the importance of edge BA, you will do BS into AT. So that is the idea. Keeping that in mind, this is the training approach, right? So what we do is we observe that majority of the graphs obey what is known as a power law degree distribution. So in order to we stick to that and we sample and we learn what we estimate the power law coefficient, which is denoted by alpha in line 2. So for every graph, so we learn this alpha, and during steps 3, 4, 5, we estimate what would be the size of each node neighborhood sample that we want to sample using alpha. And further, what we do is during each for every edge, we compute the score, which is a product of its in degree and out degree. And during every epoch, for every node, we locally vary the size that it would sample, which is represented by NPS. And during each edge, which edge would get sampled for every node, it would be prioritized based on its the out degree or sorry, the in degree of the neighbor. So higher degree nodes are given higher probability of being sampled in this approach. And when you look at the loss function, this is what I was explaining to you earlier. So if u comma v is an edge, what you do is you want to maximize theta s into theta su and theta tv. And if for edge uv, you want to also have this value to be high. Similarly, we add one more loss explicitly on top of this terms for line 16 and 17. You would have, in case u comma v is present and v comma u is not present, which is only one directional edges, you would actually have you would explicitly add this. So whole loss comes from line 18, and essentially this is what we try to this is the the pass of training. And during inference, once we learn the W and the the L parameters, right, for the GNN, then you create a an inference graph. And if you look at the embeddings, XU and X are basically the initial embeddings. So for now, assume that we have some way to initialize the initial embeddings. And for every layer, for every node, what you do is, as explained earlier, you just, for S, you basically focus on the T's, or which are the neighbors. And for the nodes, for the T embedding of every node, you just focus on the S embedding of its neighbors. So basically, you're varying the in and out neighbors in line 4 and 5. And then you do some kind of normalization, and then you have your theta S and theta T for every node. Now you can use this for any application, and also this sort will also help you to apply for downstream tasks. Now, one step which I want to take here is, one could ask, like, how do you initialize XU and basically the initial embeddings? So in this paper, we tried out different experiments, and we observed that going with random walk based pre-training or initialization appears to give the best result. So let's look into the datasets and the results. So we experimented with 6 publicly available datasets, and ecom1 and ecom2 are proprietary datasets, which are which again correspond to a sample, right? So The directed percentage edge statistics actually will give you a picture of the diversity of the data sets that we considered. The first question that we wanted to ask is how do different models perform on these data sets, and we were seeing a significant lift in MRR and hit rate using our approach because of the explicit modeling of having these two embeddings SNT. That's one takeaway. Second is, one could ask like, you have said so much. What about the direction? How does your model handle the direction? So to answer that, we frame an edge direction prediction task, which is similar to link prediction. And we compute the AUC based on the predicted scores. And we are observing that uh, compared to Magnet, which was the best paper at, for this task at that point, we were actually seeing little lift over this baseline. And then some form of ablation, which is on the Twitter dataset. So in the table, UN are from the uniform and normal distribution, XU and XN are Xavier uniform and Xavier normal, RWR is random walk with restart. So if you observe from different data sets which we performed, we also observed the pattern that in case you don't want to rely on retraining, then the other option is just to focus on using a normal distribution. Sampling from a normal distribution seems to be giving a decent performance. And then one more question which we wanted to ask is how does this approach function on both low and high degree nodes? Is there any improvement in performance from the sampling? So you can take the extremes, which is considering all the neighbors during sampling, and the other extreme is considering the minimum numbers of nodes for each sampling. In our case, it's more of a mix, wherein for high degree nodes we try to reduce the number of neighbors, and for low degree nodes we try to take the maximum that we can. And we actually see that playing around with the value alpha, which I explained in the slides earlier, shows that this actually is a good combination for both low and high degree nodes, and we're able to get the best performance, though it's marginally visible in the slide. And the other question is that how does this sampling contribute to time during training? And we were observing that per epoch, vanilla GCN you can think of in a uniform sampling, and we are kind of like 1.5 to 2 times more in terms of training per epoch compared to a vanilla approach. And you can find more results in the paper, wherein we compared a model blade against a GAT, which one could argue is some kind of giving attention to the edge scores to the nodes based on their features. So we performed those experiments and you can find them in the paper. So, and some kind of qualitative results. So this is a kind of a model which we deployed for product recommendation. And if you see, the query product was a cream and we're actually recommending a face wash. And here you have a phone and you're recommending a bumper case. So these kind of things are, so in this setting, we have actually deployed and used our model in production. So want to conclude by saying that product recommendation problem, which is core to any e-commerce setting, we framed our application as a node recommendation problem in directed graphs. And in order to handle modeling edge strength and direction, we used dual embeddings. And to handle any structural bias in the graph, we had some kind of locally weighing and neighborhood sampling. And our approach is generic and it could be applied to any directed graph with or without edge node features. And we also did and conducted an A/B test online, and we saw very good results using this approach. Thank you.